cells here, action potentials would be generated in these contractile cells. Now remember what was different, and we'll review it here in just a second. What was different about these action potentials is that they were really long. Okay? And by that I mean that the amount of time that the sarcolemma on a myocardial contractile cell is depolarized is, 200 to 300 milliseconds, compared to a skeletal myofiber where that was only 4 or 5 milliseconds. So these action potentials are really lengthened. Now the significance of that is that increases the amount of time of what we call the absolute refractory period. So if the membrane's depolarized, it can't be depolarized again. So you can't have these rapid action potentials. In fact, the most you can get is in the neighborhood of 200 to 250 per minute. Now, as a result of that, it prevents this phenomenon of summation in the twitch. Remember, in response to a stimulus, a muscle cell will contract and relax. And if you apply a skeletal muscle cell, and if you continually apply an action potential, these contractions will be summed on top of each other. And when the result is that the force gets higher and higher and higher. And at some point you reach tetany, and that's the state of like full contraction. And because of the events that occur during tetany, that will lead to fatigue and failure. And we saw that cardiac muscle tissue never fails under normal conditions. So that's different than heart failure or something like that. But under normal conditions, it never tires. It will just keep beating and beating. And that's because we prevent summation, which prevents tetany, which prevents fatigue. Okay? And it is really the fact that the action potential is long that does that. So here's excitation, contraction, coupling, as we mentioned Friday in a cardiac muscle cell. Let me highlight what's different about this. What's different is this here. Okay. There is a special kind of calcium channel on cardiac muscle cells, just like there is in smooth muscle, that is voltage gated. And they're called L-type, and that just means slow. L-type channels are slow opening and slow closing. And as a result of that channel opening and closing, at rest, which in a cardiac myofiber is about minus 90 millivolts, this channel is closed. When an action potential on the sarcolemma travels down the muscle cell, it will affect these L-type calcium channels. And when the L-type calcium channel opens, when it's depolarized, you get an influx of calcium. The significance of this influx of calcium here is that it contributes to membrane depolarization. So as a result of the calcium influx, we'll see in a minute, the membrane stays depolarized longer. Now this calcium influx here, so calcium induced, will trigger the opening of voltage-gated ryanodine receptor calcium channels on the SR. Now that's different than skeletal because they weren't linked by a mechanical gate. It's just purely electrical. You need the calcium spark or the calcium influx from ECF to trigger this release here. And this is called the calcium spark when you get this massive flood of calcium from the SR. Once you get that, of course, it binds to troponin and displaces tropomyosin, and you get the power stroke cycle. It's identical to the power stroke cycle in skeletal muscle and smooth muscle. The 90-45 swivel is all the same. Okay? Now, for the muscle to relax, obviously there's no action potential on the sarcolemma, so it's repolarized. We need to put the calcium back where it came from. There are calcium ATPase pumps here that pump calcium back into the SR. Honestly, they're working all the time. If there's large amounts of extracellular calcium, cytoplasmic calcium, they'll just pump it back into the SR. Right? Obviously, if the channel's open, it's pumping it back, but it's coming right back out. Right? But if the channel's closed, it's pumping it back in, and now we're storing it back in here. Now, ATPase pumps, that's primary active transport, that's pretty quick. Okay? Those pumps use a lot of ATP, but they'll move calcium back into the SR pretty quickly. Okay? Now, some of the calcium came from extracellular sources, right? So some of the calcium also needs to be pumped back outside of the cell into ECF. Now here, it is not an ATPase pump that does it, but it's secondary active transport here. So remember, secondary active transport, we use the energy from diffusion of one ion to drive the active transport of another one. So look what happens here. So this is an NCX, which stands for sodium-calcium exchanger. It is an antiport secondary active transporter. So these things are going to move in opposite direction. Sodium diffuses in, right? And as sodium diffuses in, that's exergonic, that releases energy, and this protein here, pump, uses that energy to pump calcium out. Okay. Now ultimately what has to happen here, the sodium that comes in has to be pumped back out. Obviously, we use ATP to do that. There's a sodium-potassium pump that will do that. Okay, there. Now, this one here works much more slowly than this one does. I mean, that kind of makes sense, you would think, right? This one's using ATP, it's pretty quick. These secondary active transporters work, but they're slow. So the bottom line for this one is that it's going to take a while for this sodium, or for the calcium, to be pumped back into the ECF. So this calcium stays around in the cytoplasm a little bit longer. The membrane stays depolarized a little bit longer. So when we look at that action potential tracing, right, it looks something like this. Right? And this is, you know, kind of what we looked at before.